Okay, my resolve to live without an AC is being tested severely because of these incredibly warm temperatures with very high humidity, but I'll survive for now. So somebody commented on my posting on the Facebook about the climate modeling course that there is this book, Demystifying Climate Models by Andrew Gettleman and Ricky Rude, which is a good book if you want to learn about models without equations. That was not my original goal, but I figured I'll put in a few podcasts taking the most salient points from this book about demystifying climate models and go through them without the equations, as the book is intending to do. So they start with, obviously I've skipped many figures and we'll just pick some representative figures to make a few points, with some of which will overlap with what we have done, but some are new points. So they start by looking at shifting probability in terms of introducing climate models. Shifting probability distribution functions are illustrated in different ways, going from blue to the red distribution. So we have situations where you have a given climate state, let's say before the human interactions. Now I can feel some breeze, so I don't know how bad the sound is going to get, but I need the breeze, sorry. So you can just have a shift in the mean. So the mean temperatures get warmer. So March in India was a record warm month, but it is each March getting warmer. That's kind of a shift in the mean. So then you will shift the tail, so you will see that when you draw these lines and then this thin dashed, the dotted line, they are changes in distributions of temperatures above a certain threshold. You can do it as percentiles and so on and so forth. So thin dashed lines are the mean distributions and dotted lines are fixed points to illustrate the probabilities of changes, right? So here the tail gets shifted as well, so you'll end up with lots more hot and some off the scale records and less cold temperatures. So you have moved away from the colder end of the scale towards warmer end, and you moved the warmer end to much warmer tail rare events, if you would, and the mean itself has shifted. Whereas you can keep the mean the same but increase the variance, the variability around the mean, in which case you will probably end up getting more hot and cold, so both off scale mean temperatures. Even though the mean is same, you're creating tails which are more hot and cold. You can of course increase in mean and variance and end up with a lot more hot off scale and less cold temperatures. So this is just illustrative, but in terms of just why we would want to model the climate system, of course, is that there is the reason to understand how the climate system itself is working. So how the Earth system works. We have talked about this briefly, looking at the various components like the global energy budget, which drives the system within which then the energy is distributed, and timescales are set by interactions between the atmosphere, the biosphere, and you have the geosphere here, hydrosphere, and those are kind of the main spheres. You can within that think about elemental cycles. So Earth is very unique in the sense that it still has very active tectonic and geological processes which can take away elements like carbon, sequester it away, or release them either naturally through volcanic eruptions or movement of continents, etc. But also human beings are changing it, as we will see here, in terms of causes of global change. So there are lots of details here that I won't go through. We have talked about them, but we are now most worried about understanding the functioning of the Earth system because we want to be able to predict it for various decision makings, like say climate adaptation or simple weather based decisions about scheduling flights, scheduling your vacation, and so on and so forth. So there are various time scales, but we are also most interested now in projecting into decades into the future to see where we are headed with all these perturbations we are making. So anything you want to do for the future requires models. Of course, there are statistical ways of saying how the weather will look tomorrow or next year, depending on your confidence on the statistical methods. But these dynamical models basically tell us how Earth system works and give us what are called emergent solutions. So typically in small-scale engineering systems, fluid dynamic systems, you look for convergent solutions, whereas in an open system like the Earth system, you look for these emergent solutions, the solutions that you didn't expect, like let's say the ice shelves that are breaking off of Antarctica because of atmospheric rivers doing some processes that we didn't know before, right? So if you focus on those two components, I did a clumsy job of cutting out the internal part of this. I don't know if it helps. Things can be seen a little bit clearer. For example, again, atmosphere has atmospheric circulation and greenhouse effect, and the biosphere has photosynthesis, respiration, evolution, and species interactions. And in the geosphere you have something, plate tectonics and weathering and so on, and recycling of material. Under the hydrosphere you have ocean circulation and the water cycle, for example. Okay, so the outside you have energy balance, energy coming in, going out, and redistribution of heat. So the global energy budget is in there. Elemental cycles, of course, include carbon, nitrogen, phosphorus, and so on. And ecosystems then are getting feedbacks from the ocean, atmosphere circulation, and the elemental cycles, because ecosystems are involved in nitrogen cycle, phosphorus cycle, and carbon cycle, and we are perturbing those cycles directly by mining and fossil fuel burning and so on, but we are also modifying them by fertilizers, deforestation, agriculture, and so on, right? So measurable changes in the Earth system are things we have looked at already. Human well-being is often being considered as one of the things we must measure to chart our future pathways of not only reaching net zero or decarbonization, but also making sure that mitigation and adaptation, for example, are not hurting poor people more, or they are synergistic with reducing poverty and sustainable development goals and such that we talked about. Of course, there are other things like extreme weather, quality of human life, human health, wildfires, and soil quality, and so on and so forth. Right? So this is what we want to model, and we want to also model the feedbacks between the Earth system's components and human activities and the climate itself and the ecosystems. And these are again blowing up the measurable changes in the Earth system. You can now look at more details: ozone layer, greenhouse gases, airborne particles, winds, clouds, precipitation, air, water temperatures, and you have snow and ice cover changes, ocean acidification, oxygen levels, sea level rise, and nutrient levels, uplift and sinking in the geosphere, uplift and sinking of land, sedimentation and erosion. And on this side in the biosphere you have species, population, species ranges, which change with warming, life cycles and traits, productivity, biomass extinction, and so on. Within the quality of human life, you have air quality, health, disease, food availability, displacement of human populations, which is now a serious concern because of climate change, large displacements happening, freshwater quality, availability, and often access has to be considered as well. Causes of global change, of course, fossil fuel burning is one of the main things. Renewable energies, trying to mitigate our impact, innovations, so technology, freshwater pollution, and so on. And we have already talked about these human causes and non-human causes. In the non-human causes, you have solar radiation changes, Earth's orbital parameter changes, and so on that we have talked about. So we want to model the Earth system and create often what is called a counterfactual world, where human beings were not doing anything and we're not affecting the climate, and then attribute the changes, measured changes, to human impacts by then including human impacts and say whether extreme events are increasing because of human influence, cyclones, how they are changing because of human influence. So events, frequencies, distributions, probability density functions of various features like cyclones, their intensification rates, or duration, intensity, and frequency of monsoon, active and break periods, and so on and so forth. So it's a very large range of things we want to model. So I'll come back and talk a little bit more about carbon cycle modeling, kind of jump from Earth system and elemental cycle that we mentioned into some details about carbon cycle modeling, because I didn't do this explicitly in the earlier part of the course, where we looked at mostly physical modeling. I have a full carbon cycle course, of course, but there we are not talking so much about carbon cycle modeling, but various issues of carbon cycle. So we will look at carbon cycle modeling a little bit in the next podcast before moving forward to how models are built, multiple levels of complexities, how they are put together in terms of the Earth system components, and then how they are run to simulate either the past or the future. Okay, so we'll do those as we go forward.